Hi students, here now we are going to discuss about some problems how to design a Butterworth filter for different cutoff frequency. What now they have given is they have given a design a analog Butterworth filter that has a minus 2 dB passband attenuation and at a frequency of 20 radians per second. Here the passband frequency, that is ohm p equal to 20 radians per second. Okay, and for that passband frequency the attenuation is alpha p, which is equal to 2 dB. Here there is no need to represent minus, this represent attenuation. Okay, so alpha p is equal to 2 dB and ohm p equal to 2 radians per second. Similarly, the stop band attenuation is alpha s, which is equal to minus 10 dB. So here there is no need to include minus, so plus 10 dB and a cutoff frequency of ohm c, that is 30 radians per second. Okay, so according to the design, let's see the design here. Design step, what is the first step? We need to design the order of the filter. We know the formula for the design the order of the filter. N is greater than or equal to log of square root of 10 power 0.1 alpha s minus 1, 10 power 0.1 alpha p minus 1 divided by log of ohm s by ohm p. This is the formula. So now substituting the values, 10 power 0.1 alpha s is 10, right? 0.1 into 10 minus 1 divided by 10 power 0.1 into alpha p is 2 minus 1 divided by log of ohm s is what, 30, and ohm p is 20, so 30 by 20. So simplify this, what you will get is you will get 3.37. so whatever it may be, you need to equate to the next nearest integer. So the next nearest integer is 4. Okay, next here we have find out the order of the filter is 4. Now see the design step, we have done these two steps. Now we are going to find out the h of s for ohm c equal to 1 radians per second. Okay, in the last class itself we have derived the steps, right? For n is equal to 4. So this is what the thing we have derived for n is equal to 4 for omega, that is ohm c is equal to 1 radians per second. So for n is equal to 4, the normalized here, what we are, this is the normalized low pass filter. Here h of s is equal to, that is 1 by s square plus 0.7653 s plus 1 into s square plus 1.84776 s plus 1. So this is what your h of s. From this procedure, what you need to do is you need to write all these steps in this here in the next step. Okay, so we have done so already, so I am incorporating that answer here. Okay, so now this is what the transfer function. Okay, so I have done third step. Okay, now see the fourth step. What is the fourth step? You need to calculate the cutoff frequency ohm c. We need to calculate the cutoff frequency ohm c. The formula for this is ohm p by 10 power 0.1 alpha p minus 1 the whole power 1 by 2n. So here ohm p is 20 divided by 10 power 0.1 alpha into 2 minus 1 the whole power, n is 4, so it is 8. So when you find out this, it is 21.3868 will be your answer. Okay, now we have find out cutoff frequency. The next step is we need to find out the HA of s for this cutoff frequency. How we will obtain this? By substituting s is equal to s by ohm c wherever you are having s. So take so substitute wherever you are having s by ohm c. Here ohm c what we derived is 21.38. Now we need to simplify this. How we need to simplify is take LCM. So s square plus 0.16537 into 21.3868 s plus 21.3868 the whole square. So numerator 21.3868 the whole square. So here what you will get is 21.3868 the whole square divided by s square plus 1.8447 into 21.3868 into S plus 21.3868 the whole square. So when you simplify these values, so what you will get is here 0.20921 into 10 power 6 divided by S square plus 16.3686 S plus 457.394 into S square plus 39.5176 S plus 457.394. So now this is what the desired transfer function for the given specification. So now see this problem. For the given specification, you need to find the order and you need to design the transfer function of the Butterworth filter. They have given alpha p, alpha s, but instead of this ohm c and ohm s, ohm p and ohm s, what they have given is they have given fp. So it is nothing but we know that omega is equal to 2 pi f, right? So this represent digital frequency. Here this ohm represent analog frequency. That is the difference. So 2 pi into fp, which is equal to 2 pi into 1000, so which is nothing but 2000 radians per second. Here ohm p is this is ohm p and this is ohm s. Okay, so ohm s is equal to 2 pi fs, which is equal to 2 pi into 2000 kilohertz. So 2000 pi here. So 4000 pi radians per second. So using this, you proceed with the previous procedure and find out the transfer function. So this is your tutorial problem. Okay, so already I have given tutorial problem to find the order of the filter for different values, to find the transfer function of the filter for different values of n. So the next thing is you are going to solve this problem. Okay, so this is the one of the another method of giving the specification. So first one is just they will directly give the cutoff frequency, that is they will give the ohm p ohm s, otherwise they will give that is the angular frequency. Here they will give the cutoff frequency fp fs. Okay, so from this we need to find ohm p ohm s, and you need to proceed in the same manner as we did it, and you have to solve this one. Now this was the another method of giving the specification. Okay, so here what they have given is they have given some range for this frequency range and this for this frequency range. Okay, so here if we want to, what is the first step? We need to find out the order of the filter. The order of the filter is this n greater than or equal to lambda by epsilon log of ohm s by ohm p. We know that this is 10 power 0.1 alpha p minus 1 the square root. Okay, so here what we have to do is in this we are going to equate the right. So this is what we are going to consider is we are going to consider 1 plus epsilon square is equal to 0.1, and this we are going to consider square root of 1 plus lambda square is equal to 0.2. Okay, so what is the meaning of this is, so here this is the ideal characteristic. So you will have some ripples like this. Okay, so this is the minimum ripple value, so related to the pass band. Okay, so 1 plus epsilon square, so and this is related to 1 by 1 plus square root of lambda square. Okay, so this is the minimum ripple value we are going to consider. So here I am going to consider this value. So from this you need to find out epsilon. Here we need to find out lambda. So this can be written as 1 plus epsilon square is equal to 1 divided by 0.9. So from that when I find epsilon, it is 484. So another thing is here, from this when I do it in the similar manner, I will get lambda is equal to 0.4898. Okay, now we have to substitute in this equation, and here we need to know the cutoff frequency ohm s by ohm p. Here ohm s is nothing but this one. Okay, so ohm s is nothing but 0.45 and ohm p is nothing but this one 0.24. So because this is the parameter related to passband frequency and this is the parameter related to stopband frequency, so here this represent ohm p and this represent ohm s. Okay, so here now ohm s is equal to 0.45 and ohm p is equal to 0.25. So 0.45 by 0.25. So what you will get is, you will get again 3.34. Previous problem also we got this. So this is equal to 4. The same transfer function I am going to take, that is 1 by s square plus 0.76553s plus 1 into s square plus 1.8477 s plus 1. So this is the transfer function of the filter. Next we need to design the cutoff frequency. This cutoff frequency is nothing but ohm p by root of 10 power 0.1 alpha p minus 1. Okay, so this is what your formula, right? So here we are not having alpha p, so but we know this is equivalent to epsilon, right? So here it is epsilon the whole power 1 by n. Okay, so here because this is square root 1 by 2, so you will get 1 by n. So here 0.2 pi divided by 0.484 the whole power 1 by 4, which is equal to 0.754. Okay, so here the cutoff frequency is 0.754. So now what you need to do is, you need to substitute s by this cutoff frequency value in this and you have to find out hs. So this is also in one of your tutorial problem. Complete this one and we will discuss the results in the next class. Sorry, in this here there is one correction. Here we have designed that in this ohm c is equal to ohm p divided by 10 power 0.1 alpha p minus 1 the whole power 1 by 2n. Okay, now we are having epsilon, where epsilon is equal to 10 power 0.1 alpha p minus 1 the whole power 1 by 2, right? So ohm p divided by 10 power 0.1 alpha, here instead of this what we need to substitute is, we am going to substitute alpha 1 by n, correct only. So here the same thing I have done, sorry, here the same procedure here. So 0.2 pi by 0.484 the whole power 1 by 4, so it is equal to 0.754. so the using this you find out the transfer function of the filter. Okay, so this is what your tutorial, you need to solve it and find the transfer function of the filter. Okay, that's what about the design of an analog Butterworth filter. Only 3 different methods of giving the specification, so remaining procedure and all same. So I will post you some of the solved problems, so you try using that. Thank you.